Hi! Today's lesson is about the different types of bonds that hold atoms together. Earlier this year, we had learned to look at models where different shapes were indicative of different atoms, of different elements, and when those shapes or atoms were touching each other, that was meant to represent a chemical bond. Today we're going to investigate what different elements will make a certain type of bond. Chemical bonds are ultimately attractive forces between atoms. Attractive forces between atoms. And there are three types that we're going to learn about. Three types of bonds. The first is called a metallic bond. The second is called an ionic bond. And the third is called a covalent bond. The covalent bond can be further categorized as either a polar covalent bond or a nonpolar covalent bond. And we will elaborate on each of these three types of bonds as the lecture continues. Looking at the samples of matter we have in the pictures here, as you look, they're all samples of metals. Each of these metals, remember, they're made up of billions and billions and billions, or moles and moles worth of atoms. Yet there's got to be some kind of attractive force holding those atoms together, and we call them metallic bonds. So metallic bonds hold atoms of metals together. Metallic bonds hold atoms of metals together. Well, let's remind ourselves what the structure of the atom looks like. We have a nucleus, and I know it's the outdated model, but it really is best if we try to represent it using the Bohr model, with the energy levels surrounding the nucleus. What part of this atom do you suppose is doing the bonding? Well, what we learned last lesson is that within an atom itself, the attractive force will be between the positive protons in the nucleus and the negative electrons in the cloud. But what is it that makes one atom bond with another atom? And that has to do with the valence shell. It is absolutely imperative before we get any further that we all understand it's the valence electrons that are the ones involved in bonding. Again, it's imperative to know that when we talk about atoms bonding, that it's the valence electrons in the electron cloud that are involved in this bonding process. The valence electrons are the ones involved in bonding because they're the ones that are furthest away from that positive attraction in the nucleus. So they're going to be able to be lost or gained, as you'll see as we continue with our lesson. So what is it about the valence electrons in a metal that allows these metallic bonds to form? Well, it brings us to this idea of what are referred to as delocalized electrons. delocalized electrons. Delocalized, meaning the electrons in the valence shell are not fixed with one particular nucleus of the metallic atom. The electrons are allowed to move from one nucleus to another nucleus to another nucleus. The best way chemists know how to describe this is by referring to it as a sea of mobile electrons, it being a metallic bond. A metallic bond is described as a sea, and sea meaning like ocean, of mobile electrons. A metallic bond is a sea of mobile electrons. The ocean or the sea is in constant motion. It has currents that are constantly moving the water molecules around. And that's what's going on in a metallic bond. These valence electrons are constantly moving from one nucleus to another nucleus to another to another. And as a result, this explains the properties of metals. The sea of mobile electrons is explaining the properties of metals. We said last unit that metals are good conductors of both heat and electricity. That's because these mobile electrons that are moving from one nucleus to the other kind of wear the heat or the electricity as if they were carrying a backpack around the hallways of the school. And they just travel with that, backpack of energy or that backpack of heat and are able to move it from one nucleus to another to another. It also can explain why metals are malleable. Malleable, if you forgot, means that we can hammer the metal, we can bend it, we can shape it, and it's not going to break. That's because the electrons are able to then shift. There's no rigidity to the electrons in the metallic bond. So they just kind of shift and shape and they move as we need them to. And that also explains how metals are able to be drawn into a wire. That's where metals are described as being ductile. And if you look at the picture here on the right, we have examples of that. You can draw out or stretch the metal into these thin wires because the electrons are not rigid. They are a sea of mobile electrons. There's this current of constantly moving electrons from one nucleus to the next to the next. That's our first type of bond, metallic bond. And you will find these between atoms of metals. Let's move on to the next type. The next type of bond is called an ionic bond. And to give you a little bit of background, let's revisit what we know about the periodic table of the elements. To the best of your ability, sketch a periodic table of the elements. Mine is not perfect, and yours doesn't have to be either. What I would like for us to emphasize are the groups. And we'll do the S and the P blocks. 15, group 16, group 17, and group 18. A friendly reminder, some patterns that we learned last unit. Any of our elements in group 1, their valence shell is going to say S1. All of the elements in group 2, theirs are going to say S2 for the valence shell electron configuration. My elements in group 13 will say S2P1. Group 14 says S2P2. And I'll continue down the list until my P block is all the way full. And remember that we do have helium up here, where Helium's configuration is simply going to be the S2, 1s2. Now, with all of bonding, not only is a guiding principle that the valence electrons are going to be involved in it, but it's also that every element is striving to have the valence shell configuration of a noble gas. Key concept here. All elements strive to have a full valence shell. Let's say it again. All elements strive to have a full valence shell. So looking at my elements in group 1, they have a choice. They can either gain 7 electrons, or they can lose 1. Which do you think nature's going to prefer? Well, remember we have a guiding principle that nature likes low energy. So if my elements in group 1, hydrogen and the alkali metals, want to get a full shell, hydrogen would either need to gain 1 to look like helium, or it could lose 1. And all of my alkali metals can either gain 1, 2, 3, 4, 5, 6, 7 to get a full shell, or they can lose 1. Nature is going to prefer that they lose 1. My elements in group 2, the alkaline earth metals, they have 2 valence shells already. Valence electrons, excuse me. They can either have the choice to gain 6 electrons or lose 2. Which do you suppose nature would prefer? You're right, losing 2. That takes less energy to lose 2 electrons than it does to gain 6. Elements in group 13 have 3 valence electrons. They can either gain 5 or lose 3. Nature's going to prefer to lose 3. Elements in group 14 have 4 valence electrons. They can either gain 4 or lose 4. Meh. Kind of a what-if situation. My elements in group 15 have 5 valence electrons. They can either gain 3 or they can lose 5. Nature's going to prefer that they gain 3. The oxygen group, the elements in group 16, have 6 valence electrons. They can either gain 2 to have a full shell, or they can lose 6. Nature would prefer that they gain 2 electrons. The halogens have 7 valence electrons. They can either gain 1 or lose 7. Nature's going to prefer that they gain 1 rather than lose the 7. Now, thinking back to last unit, this also goes along with the ionization energy and the electronegativity. We had said that metals tend to have low ionization energy. As a result, they're going to lose their electrons. Metals have low ionization energy and will lose their electrons. Whenever an atom loses an electron, a cation will form. Last unit, we also learned that atoms that have a strong electronegativity or a high electronegativity are going to be very likely to gain electrons, and those would be our nonmetals. The nonmetals have high electronegativity and will gain electrons. And whenever an atom gains an electron, an anion forms. These positively charged cations and the negatively charged anions are going to wind up attracting each other. And what forms is this ionic bond. The root ion is part of the description. So an ionic bond forms between atoms of a metal and a nonmetal, because there's a gain/lost of electrons. Repeating that, an ionic bond forms between atoms of a metal and a nonmetal because there's a gain/lost of electrons. The metal loses electrons to the nonmetal that gains it, or gains them, that gains the electrons. When a metal loses electrons, a cation forms. Cations, that T looks like a positive sign. It's a good way to remember it. And the nonmetal that gains, that's going to form an anion. Some people like to think when you write a capital A, that cross for the letter A is where you get the reminder that anions are negatively charged. I don't know, it works for some people. Other people like to think of it as a negative ion. I don't know. Maybe it'll work for you, maybe it won't. But ultimately, that electrostatic attraction between the positive and the negative is what forms our ionic bond. To give you a picture or a model of what that would look like at the particle level, these pictures here try to show you an ionic bond. Notice that there's no like sticks or anything. The electrons aren't moving. We automatically know that the electron has been transferred. We know that the smaller particles are the cations, because when we lose electrons from the valence shell, that valence shell disappears, and now the nucleus has a greater effective nuclear charge. That valence shell is now completely gone, hence the cation is smaller than the original atom. And we know that the larger sized particles are going to be our anions, because when we gain electrons to the electron cloud, now the electron cloud, or the negative charge, dominates compared to the effective nuclear charge of the nucleus, and the repulsion within the cloud is going to dominate. And that repulsion means the electrons move away from each other and the size gets bigger. So when we're trying to model what an ionic bond looks like, it's literally these positive and negatively charged particles that just attract to each other. It's an electrostatic attraction. What it looks like in real life are the three pictures we have here. The properties of ionic solids I just kind of ruined it for you. Ionic compounds, excuse me, is you'll tend to notice that they're mostly solids. Those cations and anions have such a strong attraction to them that they're going to have particles touching each other, ergo, the solid state. The attraction is so great that they're also going to have very high melting and boiling points. That's a fun fact about metals too. High melting and boiling points. Let me go back to the metallic bonds here and just make a note of that as well. It's not necessarily explained by the sea of mobile electrons, other than the fact that everything has a very strong attraction as well. High melting and boiling points for solids, metallic bonds. Getting back to the ionic bonds. I also want you to know, fun fact about chemistry, that whenever you hear the word salt, it's describing an ionic compound. So in chemistry, salts are a classification of chemicals. I know all of us automatically think of table salt, NaCl, sodium chloride, but there are other salts out there as well. The picture on the right is copper 2 sulfate. The picture in the middle, I believe, is Himalayan salt. And the picture on the left is sodium chloride. They're mostly crystalline also. They have this beautiful crystal-like structure to them. And that would be evident as you look at the arrangement of the cations and the anions, how they sort of arrange themselves in a crystal formation. This brings us to our third and final bond type, which is that of the covalent bond. Covalent bonds are found in all molecules. So when you hear the word water molecule, you automatically know that those atoms are going to be held together with a covalent bond. It's sort of like a hidden meaning. Whenever you hear molecule, boom, you know exactly what type of bond it is. Well, speaking of water, when we look at our periodic table of the elements, H2O, remember, it doesn't have to be perfect, hydrogen, oxygen, those are both nonmetals. And when you think about what we developed or rationalized just a moment ago when we were talking about ionic bonds, we had said that the nonmetals are going to want to gain electrons. Well, that's all fine and dandy when you're paired up or bonded with a species that's willing to lose its electron. But what if you have the situation like we do with water, where we have two nonmetals, both of which want to gain electrons, right? They want to gain electrons. But if you've got no one you're paired with who's willing to lose the electrons, the only way you can each be stable, happy, satisfied with a full valence shell is if you compromise and share your valence electrons. And that is how we define covalent bonds. The valence electrons are shared between atoms of nonmetals. Again, when you have more than one nonmetal making a molecule, Because all nonmetals want to gain, the only way they're able to have a full valence shell is if they compromise and share the valence electrons. Now, as we all know, there are two kinds of sharing. There's the kind we're supposed to do. We're supposed to have an equal sharing, right? When you have a situation where you've got friends hanging out and you're, playing your PlayStation or you were playing Barbies or something, you should be sharing the time equally. But that isn't always the case. So we have the second situation where we have unequal sharing of the electrons. And determining whether we're sharing equally or unequally is all 100% based on the electronegativity difference. Based on the electronegativity difference of the atoms in the molecule. Electronegativity, a friendly reminder, is an arbitrary scale that chemists came up with. It's a number line that goes from 0 to 4. Fluorine is the highest with a value of 4. And our noble gases have a value of 0 because remember, they already have a full shell. So they have 0 ability to gain an electron because there's no place for it to go. Its valence shell is already filled. So if we have the situation where we've got two nonmetals that have similar or exactly the same ability to gain electrons, they are going to wind up in this equal sharing scenario. And that is called a nonpolar covalent bond. A nonpolar covalent bond. In other words, they have nearly equal ability, or equal, so I'm going to put nearly in parentheses. Nearly or equal ability to gain electrons. If we have the scenario where one nonmetal is a much better gainer of electrons than the other, then we're going to have the scenario of unequal sharing. And that's referred to as a polar covalent bond. A trick that I have to remember this, maybe it will work for you. When I hear polar, I think polar bears, cold weather. In order for me to get warm, I'm going to want to hog the blanket, hog the covers, etc. Hogging is what we mean by unequal sharing. I'm not being nice. I don't want anyone else to have my blanket. I want to keep it for myself because I'm cold and I'm living with the polar bears. Non-polar means I'm not cold, so now I am willing to share my blanket. Hopefully it helps you. But to try to describe in words what the polar covalent bond means, it means that the one atom will hog the electrons because it has a greater electronegativity. So how am I going to know what equal or nearly equal is? Or how will I know when one atom hogs because it has a greater electronegativity? Well, that brings us back to this little number line that I drew over here. Excuse me. The cutoff is understood to be 0.4 or 4/10. No, wait, no. Let me give you a different number line. Here's your electronegativity difference scale. Electronegativity difference scale. Ooh. Again, it'll go from 0 to 0.4, and then I'll even go so far as to say 1.7. And this is not necessarily cut in stone, this 1.7. It ultimately has to depend upon whether you're metals or nonmetals. But in any event, if you are within the range of, bring back my math here, equal to 0, equal to 0.4, that range in there, that's going to be your nonpolar covalent bond. If you are equal to or greater than 1.7, that's going to be an ionic bond. But remember, we have to double check metal, nonmetal for it to be ionic. And if we're in the middle here, so if it's like 0.5 to 1.6, that's where will be a polar covalent bond. And what this scale is trying to tell you is that if the difference is 0, it means they're sharing perfectly. They're sharing equally. There's no difference in their electronegativities. They both have the same ability to gain the electrons. As you move further and further up the scale, we get some more hogging of the electrons, and eventually we get to a point where the hogging is so great that we have a complete transfer of electrons. And when that happens, the ions are formed, and ergo an ionic bond forms. So when you look here, water, ammonia, carbon dioxide, methane, these are 4 examples of molecules, right? A molecule would be this cluster. Those are molecules. And the sticks in here, those are trying to represent the covalent bond. And it's occurring from the sharing of electrons. How do I know if they're shared equally or not? You have to go to your reference packet. The reference packet chart A, or table A, gives you the electronegativity values. So for example, oxygen's value, its electronegativity value is 3.5. Knowing that it's a scale of 0 to 4, that's a really strong ability to gain electrons. It's close to 4. Fluorine is the highest, remember? Hydrogen's is 2.2. Granted, I'm doing this from memory. So if I'm wrong, please correct me. It may be 2. In any event, when I literally take the difference means subtract. The difference is 1.3. In other words, oxygen is such a better gainer of electrons than hydrogen is that it's going to hog the electrons. The oxygen atom is going to hog the electrons. They're still sharing. It's just they're not sharing evenly. So in summary, the 3 bonds types are metallic, ionic, covalent. How do we know when they are in existence? Well, if you have a sample of a metal, you know that a metallic bond is holding those atoms together. If you have a sample of matter that's comprised of metals and nonmetals, you know that there's been a transfer of valence electrons in order for the ions to form, and an ionic bond exists. If your sample of matter has only nonmetals, then you know you have a covalent bond and the valence electrons will be shared. There is one disclaimer, and that's back with our ionics, because we have the existence of what's referred to as polyatomic ions. Polyatomic ions. They are molecules with a charge. Polyatomic ions are molecules with a charge. We just learned a few minutes ago that molecules implies that the atoms are held together with covalent bonds. However, collectively, the grouping of them has either gained or lost electrons. For example, hydroxide. That's a polyatomic ion. It's an oxygen atom and a hydrogen atom, both nonmetals. So you know that these are going to be bonded with the sharing of electrons. But all together, the only way that they can share their electrons and have a full shell is if those two atoms collectively gain one electron. This can be found in the reference packet. I think it's chart C. Let's put a question mark next to that because it might be B. Anything listed in there is a polyatomic ion. That word ion means that it is going to be held together with an ionic bond. However, the cluster is held together with covalent bonds. Looking at this structure here one more time, this is copper 2 sulfate. This conglomerate here, the sulfur and the 4 oxygens, that's a polyatomic ion. Because the sulfur and the oxygen are nonmetals, those atoms are held together with a covalent bond. However, they cannot have full valence shells unless collectively they have gained 2 electrons. We'll elaborate on this in our next lesson when we learn how to visualize or draw these bonds. But just to let you know in summary, right? Going back to our shapes and our models, individuals, spheres, shapes, colors are meant to be atoms. When they are touching, or maybe we're using what's called the ball and stick model, and they're held together with covalent bonds, it's called a molecule. When we have the formation of ions, that has to be held together with an ionic bond due to the electrostatic attraction of the positive and the negative. If one of those ions is also a molecule, which is called a polyatomic ion, ultimately it's still an ionic bond. However, those atoms of the polyatomic ion are held together with covalent bonds. Let's practice recognizing whether metallic, ionic, or covalent bonds exist by doing an independent practice problem worksheet right now. Thanks so much for listening.